Okay, let's get started today. We will start a new chapter, chapter 4, which is called commonly used distribution. Okay. So in chapter 2, we learned property functions. For example, for discrete variables, we have property mass function. Okay. And for continuous variables, we have property density function. Okay. And today we're going to learn, in this chapter, we learn some of the commonly used distribution, including binomial distribution, Poisson distribution for discrete variables, and the famous normal distribution for continuous variables. Okay. First, let's look at discrete random variables. Okay. Again, discrete random variables takes on only a finite or countable number of variables. Okay, and we have three normally used discrete property distributions. Okay, but in this class, we're going to discuss the first two, which is binomial distribution and Poisson distribution. Okay, but before we do that, let's look at the simplest case for discrete random variables, which is called Bernoulli random variable. So this is similar to the old example of toss the coin, and the chance we get head or tail is equal to 50%. Okay, so let's look at the Bernoulli random variable first. So we use Bernoulli distribution when we have experiment which can result in one of two outcomes. So there are only two possible outcomes. Okay. One outcomes can be labeled as success, and the other outcomes can be labeled as failure. Okay. For example, we toss a coin, we can define head as success, and then the tail will be failure. Okay, so but only two possible outcomes, head or tail, no other possible outcomes. And the probability for the success is written by P. Okay. P doesn't have to be 50%, like in the case of toss of white coin. Okay, now, P could be anywhere between 0 to 1. So if the success probability is P, then the probability for the failure is 100 minus P, right? Okay. So such a trial is called a Bernoulli trial. For that Bernoulli trial, we should also mention the success probability P. Again, P could be 0.5 or could be any value between 0 to 1. Then let's look at some of the example. Okay. So the simplest one is toss a coin. So we have two possible outcomes, heads or tail. So if we define heads to be a success outcome, then P is the probability that the coin comes up heads. For normal coin, the P value is equal to 50%. So we have 50% chance we have a tail, and 50% we have a head. Okay. Another example of Bernoulli trial here says is the selection of component from a population of components. Okay. For example, some of these components are defective. So if we define success to be, we pick a defective component. For example, if 10% of this whole population is defective, then if we define success as defective component, then P is equal to 10% or 0.1. So P is a proportion of defective component in the population. Okay, so here are two examples of Bernoulli trial, Bernoulli experiment. The only parameter is p-value. Again, p-value could be 0.5 in the case of toss a coin, or could be anywhere between 0 and 1. Okay. So for any Bernoulli trial, we define a random variable x, okay, as follows. If the experiment results in a success, okay, then we say x equal to 1. Okay. Otherwise, x equal to 0. Okay. Only two possible outcomes, 0 or 1. No other outcomes. Okay. And it follows that x is discrete random variables. Okay. And the probability mass function, PMF, is defined here. So P0 means the probability for x equal to 0, okay, which is failure is equal to 1 minus P, because P is the success rate. And P1 means the probability for x equal to 1 is equal to P, right? And Px equal to 0 for any value of x other than 0 or 1. Okay, because there's no other possible outcomes, only two possible outcomes. X could be 0 or 1. Okay. For any Bernoulli trial, we should write x follow Bernoulli p. P is the probability for success. Okay, and the mean value for a Bernoulli trial, okay, is equal to P. And the variance sigma x squared is equal to P times 1 minus P. Okay, so this is based on, for probability mass function, the equation to calculate mu x and sigma x squared. Okay, let me just show you the details. Share my iPad again. Okay, so we are here. Okay, so if we find out an experiment follow a Bernoulli trial with probability of success of equal to P, okay, then the mean value of mu x will equal to P, okay, and the variance sigma x squared is equal to P minus P times 1 minus P. Okay, so this is based on the equation for mu x for discrete variables. So that's the sum of x times P for x equal to x. Okay, so that's the equation from chapter 2. Variance, the equation for variance, if you remember, is this. The variance is equal to the sum for x, okay, from 1 to n. Okay, so x minus mu x square P x equal to x. Okay. So because the probability of x only has two possible outcomes, 0 and 1. Okay, so when x is 0, the px is equal to 1 minus p. When x equal to 1, px equal to p. Okay, so that's why we get mu x is equal to p. Right? And for variance of x, it's the same thing. So when x equal to 0 minus mu x, okay, mu x equal to p square times the probability for x equal to 0, which is 1 minus p. Okay, so this is how we get the mu x and the variance. So just remember, for a Bernoulli trial, the mean value is p, and the variance is p times 1 minus p. Okay. And then let's look at example here. So 10% of component manufactured by certain process are defective. So 10% here. Component is chosen at random. Okay. X equal to 1 if the component is defective. X equal to 0 if it's not. Okay, so what is distribution of X? This is a classic Bernoulli trial. Okay, we should write X follows Bernoulli. Okay, P. Here, P is equal to 0.1, 10%, right? So X follows Bernoulli 0.1. Okay. And then what is the mean value and the variance? Okay. The mean value is P, variance is P times 1 minus P. Okay. So the mean value is equal to P, which is 0.01, and variance is P1 minus P. Okay. So turned out to be 0.09. Okay, so we read the questions, and for that question, we figure out which type of distribution the question follows. Okay, here is the simplest one. We figure out the experiment follow a Bernoulli trial with p-value of 0.1. Okay, then the remaining things will be easier. We can calculate everything follow the equation for Bernoulli trial. Okay. All right. So then let's look at the second discrete variables functions, okay, which is called binomial distribution. Okay. So if a total of n Bernoulli trials are conducted, so if the experiment consists of n Bernoulli trials, and if the these n trials are independent to each other, and if each trial has the same success probability p, so p does not change, okay, for these n trials, and if x is defined as number of success in this n trial, okay, and then we can conclude that x follow a binomial distribution. Okay, so we write x follow bin. Bin is for binomial. So for binomial distribution, we have two parameters, n and p. Okay, so n is the number of trial, and p is the success probability for each trial. So binomial and p. Okay. So we have dealt with some of the binomial distribution before. Okay. For example, we toss a coin n times. Okay. So the coin toss experiment is a simple example of binomial random variables. Okay, because each toss of coin is a Bernoulli trial. We only have two possible outcomes: success or failure, head or tail. Okay, and we toss a coin n times, and each time the success rate P doesn't change. So toss a coin n times is a classic binomial distribution. Okay. So like here, so here shows we toss a coin three times. Okay. And if we define x is the number of heads. Okay. So based on counting method, we know the first toss we have head, tail. Then for each one of these, we have again head or tail, head or tail. And then for the third toss, we have head, tail, head, tail, head, tail, and head, tail. Okay, so and then we can count because x is the number of heads. Okay, so x equal to 0. So we have 8 totally possible outcomes. Okay, so 0 means we have 0 heads, which means it is tail, 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 TTT. Okay, so the chance is 1/8. Okay, so for one head, okay, for one head, could be tail, head, tail, tail. Okay, or tail, head, tail. Okay, so you can do the count, and the probability is 3/8. So based on counting method, we can get the probability mass function for this experiment. Okay. And again, the sum of all these possible outcomes should equal to 1. Okay, make sure it's equal to 1. Okay, so we can define this experiment as binomial NP. Okay, so because n is equal to 3, p is equal to 50%. Right. So as long as we can figure this out, we can easily calculate, for example, what is the probability that we have 2 heads or we have, 1 heads or less or equal to 3 heads, for example. Okay, so yeah. Here's another example. A fair coin is tossed 10 times. Okay, so x is number of heads. What is distribution of x? Okay, so n is equal to 10. Okay, and for each of these 10 tosses, the success rate is constant, which is equal to 50%. Okay, so we see x follows binomial NP, n is 10, p is 0.5. So binomial 10, 0.5. And we can easily calculate what is probability we have less than 8 heads or more than 7 heads. Okay. Yeah. So in real life, many situations, experiments similar to the coin toss, but the p-value doesn't necessarily equal to 50%. Okay, so here is another example. So we have a sample of 10 concrete specimen, which is embedded with steel rebar. Okay, so we call that steel reinforced concrete. You're gonna learn how to design reinforced steel, okay, and then learn about concrete materials in future classes. Okay, so here we have 10 reinforced concrete, and because the specimen is exposed to corrosive environment, so the steel may be corroded. Okay, the researchers count the number that show corrosion signs. So this experiment is similar to the Cohn's experiment. Okay, so Cohn here will be a concrete specimen. Okay, so in the Cohn experiment, we define head as success, and in this experiment, we can define the specimen corroded as success. Okay, and so on. The number of toss here, the number of specimen is 10. Okay, and we can calculate the probability. For example, what is probability 8 of these 10 specimen is corroded? So in summary, for binomial experiment, it will consist of n identical trial, and each of these trials are independent to each other. For each trial, is follow a Bernoulli trial. Okay, so only one of two possible outcomes: success or failure. Okay, and probability success P does not change from trial to trial. Okay, so P remains constant. And the probability of failure will be 1 minus P, because we only have two possible outcomes. Okay, so success is P, then failure will be 1 minus P. Okay, and they will be independent to each other. Okay, and we are interested in the number of success in these n trials. For example, the number of corroded reinforced concrete specimen in 10 samples. And here is another use of binomial distribution. Okay, so if a question or experiment is similar to this, we can use binomial distribution to describe that probability. Okay. So assume a finite population contains items of two types. Okay, so successes or failures. Okay, and a simple random sample is drawn from the population. Okay, we can draw, for example, 10 samples from a population of 1,000 samples, 1,000. Okay, then if the sample size is no bigger than 5% of the population, okay, so no more than 5% of the population, then we can use binomial distribution to model the number of success. Okay, again, going back to the corroded reinforced concrete example. See if we have so if we have 1,000 concrete samples, not samples, population. Okay, the population is 1,000 concrete. Okay, and if we take a sample, if the sample size is less than 5%, so if the sample less than 5% of the population, so in our case, so 5% times 1,000, so that is 50. So if we take less than 50 concrete samples, right, and then we can use binomial distribution to predict how many of these 50 samples are corroded or not. And here's another example. So a lot contains several thousand components, okay, and 10% defective, and 7 components are sampled from the lot. Okay, so that's the sample size. Sample size is 7, and X represents the number of defective components in that 7 sample. Okay, So what is the distribution of X? Okay. So from the questions, this is a perfect binomial distribution. Okay. So S follow binomial N P, where N is equal to 7. Okay, so we pick 7 samples from several thousand. Okay, and we know the sample size is less than 5% of the whole population. Okay, so it's followed up by binomial, and P here is equal to 0.1. Okay, because X represents the number of defective components, and the probability for defective is 10%. So that's why P is equal to 0.1 here. Okay, so we know it follow binomial distribution 7, 0.1. Okay, so we can calculate, for example, the probability for these 7 samples. Okay, so X less or equal to 4. Pretty easily. Okay. How to do that? Okay. We'll discuss in the following slides. So here is probability mass function for binomial distribution, and the mean value as well as the variance. So if we figure out X follow binomial NP, and the probability mass function will be this. So Px, okay, so here is the PMF. The factorial of n over the factorial of x times factorial of n minus x, p to the power of x times 1 minus p to the power of n minus x. Okay, you don't have to know how come out with this equation. Okay, but actually based on the counting method from chapter 2, we can do that. Okay, for example, this part is Cxn. Okay, so the probability mass function will be like Cxn times p to the power of x times 1 minus p to the power of n minus x. Okay. So this is based on the counting method. Okay. So if we have n trials, okay, the total number is n. Okay, and x is success. Number of x, a success is x. Then n minus x item will be failure. So the first step will be we pick x from these n samples. Okay, so this is Cxn because in that case the order does not matter. Okay, and then the next step we're gonna figure out for this x success, the probability will be p times p times p times p, and the total number of success is x. Okay, that's why we have this part. And then the next step gonna be for the remaining n minus x sample, the chance for each one is 1 minus p. So 1 minus p times 1 minus p. So totally we have n minus x. Okay, so anyway, you don't have to remember all of this, but if we figure out an experiment follow a binomial distribution, and this is probability max function. Okay, for example, if we want to calculate px equal to 3, right? And n, for example, is equal to 10. You just plug n equal to 10, x equal to 3 into this equation, and you can easily calculate px equal to 3 is what. Okay. And the mean value for binomial distribution is equal to np, and the variance is equal to np times 1 minus p. Okay, here said npq doesn't really matter because q is the probability of failure, which is equal to 1 minus p. Okay, just remember this. Okay. So as long as the experiment follows binomial distribution, okay, so this is the equation for PMF. This is the mean value, and this is the variance. Okay. Here's the example of how we can use binomial distribution to calculate the probability. Okay. A large industry firm allows a discount on any invoice that is paid within 30 days. Okay. Of all the invoices, 10% receive discount. Okay. So in a company audit, 12 invoices are sampled at random. Okay. So what is the probability that fewer than 4 of these 12 sampled invoices receive the discount? Okay. So first of all, let's define X is the number of invoices get discount. Okay. And we have 12 samples. Okay. And for each of these samples, the chance it get discount is 10%. So this chance doesn't change over these 12 peaks. Okay. And each of these peaks are independent to each other. So we know it will follow a binomial 12, 0.1. So 12 here is n, p is equal to 0.1. Right. Okay. So we know it follows binomial 12.01. The question is asking fewer than 4 get discount. Okay. So fewer than 4. So that means for x less or equal to 3. Right? So fewer than 4, including 3, 2, 1, and 0. Okay. So we're going to add the chance, the probability 0 invoice get discount, or 1 get discount, or 2 get discount, or 3 get discount. Okay, so we add the probability of this together. Okay, so based on PMF here, this equation, right? You just plug in n here is equal to 12, x, depending on the number of x here. For example, px equal to 0. So that is px equal to 0 plus px 1, px 2, px equal to 3. Okay, so I just show one example. For x equal to 0, so n is 12, so factorial of 12. X equal to 0, factorial of 0. N minus x, 12 minus 0 factorial. Okay, so p 0.1 x to the power of x is 0. Okay, 1 minus p 1 minus 0.1 to the power of n minus x 12 minus 0. Okay, so this is px equal to 0. And then similarly, you can do px equal to 1, px equal to 2, px equal to 3. Okay, so it turned out 0.74. That means 97% of the chance the number of inverse get discount less than 3 will, that's the probability. Okay. The calculation seems to be complicated if you follow this procedure. But you can use your calculator to do that. Okay. Some of the calculator can easily calculate the probability. You can tell it you follow binomial 12.01, and it can calculate px equal to 0, 1, 2, and 3. Okay, so I don't really care. As long as you can figure out what distribution and what are the parameter, you can use whatever method to do the calculation. So you can do this, use your calculator. Okay. Actually, the table from your textbook, you can also use that to calculate. That's table 8.1, I believe. Okay. All right. So you see, right after you figure out what type of distribution a certain experiment follows, you can easily calculate the probability. Okay. Questions so far? All right. Okay. Right. So this slide just shows us why binomial distribution can be seen as n Bernoulli trial together. Okay. You can just read it. We know it already. So binomial distribution can be seen as n identical Bernoulli trial added together. Okay. So this slide is showing us how to estimate the proportion p. Okay. So if x follow binomial distribution np, okay, and then the sample proportion. So the sample proportion we write as p with a small hat on top of it. So p is equal to x. So x, remember, is number of success. Okay, and n is the n trial. Okay, so we can use the sample proportion to estimate the population success probability p. Okay, because every time the samples, depending on the sample, it will give a different sample proportion. Okay, so that's only an estimation. Then let's look at for this estimation, what is the bias and what is uncertainty? Okay, the bias is the difference between mean value of sample proportion minus the true value. Okay, so this is what we learned from chapter 3. Bias is equal to mean value minus true value. Okay. And let's calculate the mean value of the sample proportion is this. Okay, so that is equal to mean value of x over n. Okay, So that is because n is a constant, that will become mu x over n. Okay. And mu x for binomial distribution is equal to np. Okay. As we see from here. Okay. Mu x is equal to np. So np over n become p. So the bias is equal to p minus p is equal to 0. Okay. So we see the sample proportion is unbiased because the bias is equal to 0. Okay. Then let's look at the uncertainty. Okay. The uncertainty for sample proportion is this. Okay. And how we get that? So that's uncertainty of sample proportion is equal to sigma x over n. Right? Again, n is a constant. It becomes sigma x over n. Okay. And sigma x for binomial distribution, we can figure out from here. So this is sigma x squared. So sigma x will be square root of np times 1 minus p. Okay. So here we become square root of np times 1 minus p divided by n. Simplify that, will become, okay, become this. So the uncertainty is equal to this. As we can see, if we increase the sample size n, the uncertainty will become smaller. Okay. If the question does not tell us the population proportion, so if the p-value is unknown, we can substitute sample proportion for population proportion. Okay. Here's another example for binomial distribution. So marksman hit the target 80% of the time. So each shot, the chance hit the target is 0.8. And he fires 5 shots. So it is binomial distribution. Okay. So fire 5 shots at the target. What is the probability exactly 3 shots hit the target? Okay, so this is binomial NP. So N is equal to 5 because he shot 5 shots. For each shot, it is 0.8. Okay, so we calculate Px equal to 3. We plug in the equation. So this is C3n because x equal to 3. Okay, so it turned out to be 20% of the chance exactly 3 shots out of these 5 total shots hit the target. Okay, so we can figure out this answer quickly. If the question asking probability more than 3 shots hit the target, so more than 3, including 4 and 5. Okay, so no more, yes, because the total shot is 5. So P larger than 3 is equal to Px equal to 4 plus Px equal to 5. Okay, so plug in the value of n and x. So 74% more than 3 shots hit the target. Okay. Question so far? All right. You may wonder why this is a C, this is CXN. Okay, so P X 1 minus P and minus X. Okay. So this is the same as this one. Again, using counting method, because in total we have n trials. Okay. X of them are P, success. And then the remaining will be non-success. Okay, so the total non-success is n minus X. Okay, so we can think this as a counting method. We know we have X success, so we have X P, and also know we have n minus X, which is not success. So the chance is 1 minus P. So this is n steps. So we can calculate the total probability for this instant is P times P times P. So we totally have X1. So that's P to the power of X. And then for the remaining will be 1 minus P to the power of n minus X. Okay. However, this is only one instant. We need to figure out how many of these items are X. Okay, so how to pick X from the n total trial. So that is why we have C and X here. So that need to be times C X n. Okay, again, we can use counting method to figure out why we have this probability mass function for binomial trial. Okay. This is the last question for binomial distribution. Okay, so I think we'll stop here after this example. So we have a sample of 100 newly manufactured automobile tires. Okay. So 7 found to be have minor flaws on the tread. Okay. So 7 out of these 100 tires are defective. So that's 7% defective. If 4 newly manufactured tires are selected, so the sample size n is equal to 4. So install a car, estimate the probability that none of the 4 tires has a flaw. Okay. And also asking for the uncertainty for this estimate. Okay. First step, let's define P is the probability that a tire has no flaw. Okay. So probability a tire has no flaw. Okay. Based on the question, the sample proportion. So because out of the 100 tires, 7 of them are flawed. Okay. So the proportion has no flaw will be 97. So that is 100 minus 7. So 97 out of 100 tires has no flaw. So the chance a tire has no flaw is 93%. So the question asking for all the 4 tires on that car has no flaw. Okay. So the question is asking this: P all 4 tires has no flaw. Okay, so we can figure out X followed by binomial and P. So N is 4. Okay, the sample size is 4. Okay, and P is for each tire. The chance has no flaw is 93%. So binomial 4, 0.93. Okay, so based on PMF for binomial distribution, it is CXN PX 1 minus P N minus X. Okay, so N is equal to 4, P is 0.93. So that is equal to the sample proportion to the power of 4. Okay, so P is equal to 0.93. Okay, so no tire has flaw. 0.93 to the power of 4. So that is 0.7481. Right, so that's the answer for the first part of the question. The probability that none of the 4 tire has a flaw. And then let's look at what is uncertainty in this estimate. Okay, so for the uncertainty, for this estimate, this estimation is proportional to the power of 4. Okay, so this is a function of U. So this U is a function of proportion, sample proportion. Okay, and from the equation in chapter 3, this is a propagation of error. Okay, so that's equation 3.10 in chapter 3. So we discussed Tuesday this week. So if U is a function of fx, okay, sigma U is equal to du dx sigma x. Okay. Here, okay. So we try to find out sigma U. So this is what the question is asking. Uncertainty is sigma. So uncertainty in this estimate is sigma U, which is sigma P to the power of 4. Okay. So that is equal to du dx times sigma x. Okay. And du dx, so du is 4p to the power of 3. Okay. Sigma p. Okay. And we know the sample proportion, but we do not know sigma p yet. Okay. So we need to figure out sigma p. So based on the slides from slides 18, which is here. Okay. So sigma p is this: square root of p times 1 minus p over n. So sigma p is square root of p 1 minus p over n. Okay. And we use sample proportion for population proportion. Okay. So p is 0.93, 1 minus 0.93 over n. Okay. So n is 100. Okay. So sigma p is equal to 0.0255. So this will become 4 p is 0.93 to the power of 3. Sigma p is 0.0255. All right. So 0.082. All right. So that is uncertainty for this estimate. Okay. And the probability none of the 4 tire has a floor. Okay. 74.8%. Okay, let's stop here. Today we discuss actually three discrete variables distribution. The first one is Bernoulli, which is similar to toss a coin once. Binomial is n Bernoulli trial together. Okay, so that's the binomial distribution. That's all we discussed today. And next time we're gonna discuss the third one, which is Poisson distribution. And then the next time we'll discuss the famous normal distribution, which is more commonly used by all the other distribution we discussed together combined.